Today I wanted to continue our discussion about BGP. In the last class we came up with a list of rules on how different BGP speakers decide which particular routes they are going to use for different prefixes. And if you recall, first they look at the local preference, and if that doesn't give a solution, they look at the AS path. Okay. And then what they do is they look for the MED. So the lowest MED, the shortest AS path, the largest local pref, and then you prefer a eBGP learned route over iBGP learned one. And then of course there is hot potato routing. So hot potato routing is when a particular BGP speaker tries to get rid of the packet as soon as possible. So it sends it to the nearest exit router, a gateway router within its network, who has advertised a path corresponding to that prefix. Okay. And then of course you look at router ID. So this is just to break the ties. So let's look at an example and see how all of this works. So say we start with, let's say here there is AS500, and we'll focus on this particular autonomous system. Let's call it AS100. So suppose there is this router connected to AS500 R3. Let's say there is R1 and R2. And this is, let's say, connected to R4 in AS200. So we are just drawing the border routers. This is AS300. And let's say there is this AS600 over here, which has a particular IP prefix which it's going to announce. Let's say 142.32.6/24. That is a prefix which it's going to announce. And let's say all those machines which have these particular IP addresses actually belong to this autonomous system. Okay. So let's say that in between we've got AS400. Let me just call this R5. Okay, so let's say this is the network, and I'm not showing you the internal routers over here. I've just shown the border routers. Now let's say that this IP prefix gets advertised in to both neighbors. So it gives the prefix and it gives its own number. Right, and similarly it advertises this way. So what happens, R1 is, let's say that everybody advertises it. So this prefix gets advertised here. 32.6. And it has the AS level path. So what is the path going to be? AS 200, 300, 600. Okay. So this is the path, and also it gets advertised here. So we have the prefix. And there's another path here. And this is of course shorter. There are just 2 hops. This is the AS path. So now we have to ask ourselves, so these 2 particular advertisements have reached this autonomous system. So they have to, let's say these are all BGP routers which I am showing over here. So they have to discuss with each other, they have to tell each other what they have heard using the iBGP protocol. So they have learnt it using eBGP, okay, and they've shared it with each other using iBGP. So suppose the network administrator wants everybody to use this path rather than this one, network administrator of AS200, which we are focusing on. How are we going to do that? Okay, and you might think, why might he want to do that? Well, maybe because let's say he measures that the latency is better this way rather than this way. Even though the number of hops is smaller, maybe the latency is high, or maybe the total data rate that he can get, maybe these links are less provisioned. They allow a lower data rate than, let's say, these links over here. So for whatever reason, he wants everybody to use this upper path. Okay. So how do we do that? You might think, suppose the administrator wants everybody to do that, and the answer is all he has to do is to set the local preference of this particular route to be highest, okay, among all these 2 particular routes. So if we want all routers in AS100 to use the top route, okay, so the administrator of AS100 can set the local pref to be highest there. So what does it mean to do this? Well, it means that he has to configure R1 to add a local preference. So when R1 is advertising this route to R2 and R3, he will add another attribute called the local preference, which is higher for this one than for this one. Right? Maybe this one he leaves it to be whatever default value is added to the local preference, and this one he makes highest. So automatically using those rules, R3 and R2 will also use that particular route to send packets to this particular prefix. Okay, so that if you just want everybody to use a single path, the most straightforward way to do it is to use local preference. Okay, so suppose we want to do something else. Suppose we want all routers, all BGP routers, let's just say this. These are the BGP speakers to use the lower route so that means AS, what would it be, AS 400, AS 600. So by the top route I mean AS 200, 300, 600. Okay. So what are we? So we want everybody to use this. So how are we going to do that? Well, suppose we don't do anything. Suppose we don't set local preference. I mean, one way to do it is again you set local preference. Okay, but suppose we don't use local preference, then what's going to happen? So then everybody is going to skip this first choice. Okay, because first way to decide which path to use, and then they go to AS path and they look at the shortest one. And clearly this one is shorter. Okay, so actually if you let the local preference be the default value for both, automatically all will use this shorter path. Okay, so one way is to use local preference. And the second is to okay, so second is by default all will use the shortest path. So there's actually no need to set local preference highest. So this was an easy one. Automatically all the routers, all the BGP routers learned that this is the shortest path and they end up using it. Okay. So now let's change the situation a little bit, and let's assume that suppose there was another autonomous system in between 400 and 600. So let's say this is 500. Here's 200. So this is R3, R1 and R2. This is R5 and R4. So now we get advertisements for the same particular prefix along both parts, but they are of equal length. So this is a little tricky. So suppose we didn't set local preference to anything, and let's say that the MEDs were the same. So let's go back to this list over here. So local, this is not going to give a solution because local pref is the same. This is not going to give a solution since both are the same length. This is also not going to give the solution. Right? Of course, if one of them had a lower MED, then that would be used by all. Okay. But suppose the MED is also the same, then what are we going to do? Then we have to look at this peculiar criterion where we use an eBGP learned route over an iBGP learned one. Okay. So let's look at this. So R2 has learnt about this route through eBGP, and it's learnt about the first route through iBGP. So let's just write that down. Path 1 is through AS 200, 300, 600, and path 2 is through 400, 700, 600. So R1 has learnt path 1 over eBGP and path 2 over iBGP. Okay. So it learnt about the second path from R2, which was over iBGP. Whereas R2 has learned path 2 over iBGP and path 1, okay, over iBGP. So it's a reverse. And what about R3? R3 has learned both paths over iBGP. So according to the rules, what are they going to use? So R1 is going to use this path because it learnt it over eBGP. R2 is going to use this path because it learnt it over eBGP. And what about R3? R3 has learnt both over iBGP, so it goes to the next point. It goes to the next step of selection rules and it uses hot potato routing. So if it finds that R2 is closer than R1, it will use R2. Okay, depending on the closeness metric in terms of the interior gateway protocol. Okay, so R1 uses path 1, R2 uses path 2, and if the distance of R3 to R1, let's say, is less than the distance of R3 to R2, then R3 uses path 1. Okay, so this is a hot potato routing. And the distance, by distance I mean the IGP metric. Okay, so this is how it would work. Okay, and of course if the R2 and R1 were the same distance from R3, then it would just use the router ID of these two to decide which particular one to use, right? And for router ID, we use the lowest router ID. Okay, to just for completeness, I'll write that here. Use the lowest router ID. Okay, so it gets a bit tricky, and this is not the end of the whole task, because we have only shown the BGP routers, the border routers over here. And let's look at AS100 a bit more carefully. So suppose the internal topology looked like this, and let's say that okay, so suppose it was something like this. Let's say this is R9 and this is R11, R4, and let's say this is R12. This is R2, okay, and of course this is going to R4 and R5 in the next autonomous system. So this is what it looks like internally, and maybe these don't speak BGP. Okay, so how is it going to work? Or maybe they do, right? And so like we said, let's say for hot potato routing, R3 should be able to send it to the nearest gateway, okay, whichever one, in order to send it out. Okay, so I think this should be R1. So how does BGP interact with IGP? So what does the interior gateway protocol do? That is just the intra-domain routing. So all these different routers, right, they just announce themselves using link state routing or distance vector or whatever, right? And then they have the shortest paths to each other, and that's what's there in the table. So each of these routers has all other routers within their own autonomous system in the routing table. Okay, but at least the IGP on its own doesn't have information about external routers or IP prefixes learned from BGP. Okay, so we've got to get that working. So we look at different solutions. So the first one is encapsulation. So what is encapsulation? So suppose R3, let's say, wants to send it by hot potato routing. Okay, let's say, right? And let's say it wants to send a packet to R1. Okay, and let's say that none of these routers have any BGP information. Okay, so this is the case where it's especially useful. So suppose R9, R11, R12 have no BGP information. So all they know is how to route it to some other router within their own autonomous system. So for example, in R9's routing table, it will just have information like this. this will just have IGP information. So it will have R1, R2, R3, R11, R12, and the appropriate next hop, okay, which may be let's say R11 for R1 and R12 for R2. And okay, so of course in practice we said that each of these interfaces will have its own IP address, right? But we are skipping over that. We are just talking as if each of these routers has just a single IP address, just for convenience. Okay. Anyway, so this is what it's going to be, and there is no information about the prefix, the external prefix. This is not there at all in this particular table. So what does encapsulation do? So if R3 wants to send a packet to this particular prefix, okay, the destination IP matches that prefix, it will create another IP packet which encapsulates this. So suppose D is, let's say the IP address D is something like this, 142.32.6. Let's say 21, right? This is the destination IP address. So there is some source IP, and then there is the destination D and so on. This is an IP packet. And what R3 does, it encapsulates this packet. So it puts it like in a larger IP packet. Okay, and so this is another IP header. And this becomes the payload of the new IP packet. So it's like as if you have one envelope and you're putting it in a bigger envelope, right, with a new address. So what is the source going to be here? It's going to be R3, and it's sending it to R1. Okay. This is the destination. And of course there are other header fields and so on. So now the other routers are quite capable of forwarding this packet because they know how to get to R1. Okay, so R9 is able to forward this packet. It sends it to R11. R11 to sees the destination is R1 and it reaches here. Okay. So the packet goes this way, the encapsulated packet. Now R1 looks into this packet, it sees that it is the destination, it looks at this, and based on the other fields in the header and so on, it figures out that this packet has to be forwarded, that there's an encapsulated packet. So it removes this. Okay, so R1 receives this packet and forwards this in this particular packet. Let's say it strips off the outer layer and forwards the, let's say, the internal packet. By internal I just mean over here, right, which one, the encapsulated packet, and it forwards that onwards to R4. Okay, so because R1 knows how to forward it. So in R1's table, there is more information because it is a BGP speaker and it has in its table that R4 is the next hop. So it has the destination and the next hop. So it has R2, R3 and so on, but it also has 142.32.6/24 and it has R4 as the next hop. Okay, so this is one straightforward way of doing it when your internal routers have no idea about the BGP information. Okay. So of course it's some extra work. R3 and R1 have to do some extra work and that may cause some delay. Okay, look, because R1 has to, first of all R3 has to encapsulate and R1 has to de-encapsulate and it has to sort of strip off those headers and so on, which may cause a little bit of extra delay. So let's look at the second method, and that is called pervasive BGP. So pervasive BGP is when all routers within the particular autonomous system actually speak BGP. So now everybody has information, and so suppose we are going to assume that there is a unique exit point for a particular IP prefix. So this is an assumption we are making. So let's say that the local preference has been set so that R1 becomes the exit. Okay. And in that particular case, what we can do is the following. So every router has a BGP table where it has learnt information. So there is a prefix and there is a gateway or exit. So we can just, let's say that this R1 is the exit. Suppose this is true for all. And in addition, they have an IGP table. So the IP destination IP address, and they have the next hop. Okay, so let's say that this is okay. So let's say that we are looking at R9. So there's going to be R3, R2, R3, R1, right? R11, R12, and so on, and the next hop. Right, so now let's say that all routers have information like this. Of course, this information is going to change for different routers. Okay. But what do they do? Suppose R9 gets a packet. Okay, so R3 just simply, so let's say that R3 has somehow forwarded it to R9. Okay. So what is R9 going to do? R9 is going to look up the BGP table first, and it sees that R1 is the gateway. Then it looks up this. Right? So there is a recursive lookup. So on receiving, let's say this particular packet, there is some source and destination IP D from R3. It does a recursive lookup. So what do we do? First we look up this table. So first we see there is a match of D with this IP prefix. We look up the exit. We see in this table who's the next hop for R1, and in that case it is going to be R11. And so we forward the packet to R11. So R11 is going to do a similar thing, and we are assuming that this is true for all of them, that R1 is the exit for this particular prefix. So everybody keeps forwarding towards R1 using the interior gateway protocol. So this is another solution. So a third solution is something called tagged IGP. So how does tagged IGP work? So here there is some interaction between BGP and IGP. So BGP is going to insert routes into IGP. Okay, so it's not like they are completely separate like here. Okay, so in the first case for encapsulation, we said that even if IGP has no information at all, or a router has no information about BGP, it's still going to work. Here in pervasive BGP, we said everybody speaks BGP, so there are like two tables and you do a recursive lookup. In this case, routers need not speak BGP, but BGP can sort of add some information through capabilities given by IGP. Okay, so internal routers may not be BGP speakers. Okay. So how is it going to work? So what BGP does, it will add a tag and advertise this information. So this IGP allows this tagging. Okay. So it does not know the rules of BGP and so on, but it allows that advertisements for the interior gateway protocol, whenever you are advertising any route information, you can add a tag to it. Okay. So what is done? So let's say that R1 can insert into its own IGP it can put something like this. It can put the prefix learned from BGP and a particular tag. So the tag that it can put is, let's say, itself. Let's say the gateway. This is the gateway router. And this information is propagated by IGP. Let's say it's a link state protocol and it is broadcast everywhere. So let's say it is propagated to all internal routers that is within that autonomous system using the interior gateway protocol. So let's say that it is a link state protocol. So what happens? So let's say at R9 there is only IGP running. So there is a destination, there is an next hop, and there is a tag, and then of course there is a cost. Right? So for R1 of course it says R11 and there is some cost and so on, and R2 it says R12 is the next one, right? There is some cost, and then this information has been propagated by IGP. Okay. And what it has over here, it has the tag is R2. Okay, I beg your pardon. Let's say this for the first one at least is going to be R1. Okay, and suppose, just to make it more interesting, that R2 has also advertised this prefix but with itself as the tag. So this is announced by R2. Okay, and this is announced by, this is from R1. So now what's going to happen? So suppose R3 gives R9 as this particular packet. Okay. So R3 gives to R9 a packet with some source address, and of course D is the destination corresponding to this prefix. So what is R9 going to do? So there are these two entries. What is it going to do? It's going to look up and it's going to find two matches. And let's say that there is this match and there is this match. Okay. And then what it's going to do is it's going to look up these costs. Let's say that this is 5 and this is 10. So it's going to look these up and it's going to see these two are these two match, so it looks up the cost and it finds that this one is smaller, so it forwards it. Okay, so in this particular case, it finds the matches and forwards to the closest tag which matches, right? And this ends up in doing hot potato routing. Okay, because everybody is going to, all the internal routers, they don't know BGP, so they just keep doing this lookup and they will all send it to whichever exit router is closest to it, right? And of course you might think, what if you don't want to do hot potato routing? What would you do? Suppose you wanted to use tagged IGP and you wanted all packets to go to, let's say, R2 rather than R1. Okay, then of course BGP is going to take care of the BGP routers whom they will forward to, but then you shouldn't have a route like this over here, right? Because if this is there, then you're going to end up doing hot potato routing. So if you want to all everybody to send packets only to R2 corresponding to this prefix, you would only want BGP to insert this particular route into the tagged IGP, right? So depending on the needs, you would use one of these three techniques, right? And the encapsulation is the cleanest, but the problem is that it requires some extra work to be done for every single packet, okay? Whereas these are will allow faster lookups.